Welcome to Radio Montana. My name's Jim Halfpenny and my call sign's K9YNP. This session is sponsored by the North Yellowstone Amateur Radio Club and Park County Amateur Radio Emergency Services. What I'm going to do is provide you an overview to help you pass the Federal Communications Commission exam so that you can obtain your radio license. Now, what is this thing we call amateur radio? It's the oldest social network that there is. It's nothing more than a lot of people using radios to communicate with other people. But us hams, we do a lot of things. We have our own amateur satellites. We can talk to astronauts in the International Space Station. We control models such as boats, cars, planes by radio control. We use digital modes to communicate over the radio, and we use what we call phone. That means just audio communications over the radio. Hams are authorized to run their own TV networks. We do radio telegraphy, that's the old Morse code. Home brewing means that we make a lot of the things that we use. Hams are known for their public service at races and public events of all sorts, and in particular emergency services. And then some of the hams collect old radios and make museums in their homes of the old radios. The North Yellowstone Amateur Radio Club is in Gardner, Montana, and we participate in a lot of activities. One is called the 7QP, or the 7th Call Area QSO Party. What this means is in each state in the western part of the United States, hams go out and try to see how many different counties they can complete radio communications from. Montana has over 50 counties, and in fact, that's the most counties in any of the area. And so there's a lot of work traveling to different spots to do radio communications in a set 24-hour period. Field day is another exercise where we get out and get away from our homes, from 120-volt electricity, from the internet, and have to communicate as if there were an emergency going on. Slides here show you our emergency communication setup up on Mount Washburn in Yellowstone National Park. Hams serve. They serve for both public things such as races and emergency services. And that unit of service is known as ARES, A-R-E-S for short, but it's the Amateur Radio Emergency Service. And we serve everything from fires to hurricanes to races and public gatherings. I'm going to set some goals for tonight. We're going to learn some about radio. I want to help you get your license. My agenda is first we'll cover who's who in radio, some technical topics, then operating rules and procedures, and finally we'll go into the exam itself, how you get your license and how you get your own call sign. To be a radio operator, you have to pass the Federal Communications Commission exam. That's the only way to legally do it. And we're going to get you set to do that exam. So let's take a journey now through radio land. Everything I say here, well, my students at school always say, is that going to be on the test? And yes, I will touch on everything I say will touch on information in the test. And I might throw in a little bit extra on a few things though. Okay, who are the players in this worldwide game of radio communications? At the worldwide level, it's the International Telecommunications Union, the ITU. This is a unit of the United Nations, and they deal with information and communications all over the globe. That includes television, radio, telephones. They also deal with technical issues to coordinating well over 200 countries to use the radio. Here in the United States, our main federal entity is the Federal Communications Commission, the FCC. The FCC regulates and enforces the rules that are set, and radio operators must make their records of their communications available to the FCC on request. We are members of the Amateur Radio Service, the ARS. That's a batch of folks who are interested in radio techniques just because we're interested, and we don't get paid for it. There's no money involved, but we're into advancing our skills in technical and communication phases of the radio arts. As a member of the ARS, you are the radio operator. Your radio is your station and you run your own station. Just as any station you'd tune into on your car radio, you are your own station. And your station might simply be a handheld unit. It could be a mobile unit out in the field, or it could be a base station set up in your own home. Now, hams of the ARS are also known as ham radio operators. And what that means is, as amateurs, we don't get paid, but we are very professional in our services, and the level of knowledge is very professional within the ham radio operators. Our volunteer representative is the American Radio Relay League. This is the national group representing hams. We call it the ARRL. Our national association provides national representation to the FCC, international representation to the ITU, and it serves to keep us hams together and supported in our activities. Well, let's get on to radio itself. As you probably know, light travels in waves, and radio signals also travel in waves, and these waves are called electromagnetic waves. They run perpendicular to each other, electricity on, say, the vertical axis, and magnetic waves on the horizontal axis. And as electromagnetic waves, they travel at the same speed of light, 186,000 miles per second. Now, if we look at one wave, what we'll do is name that wave as a sine wave. That means it has a portion that goes above and below a baseline. The portion above the baseline we consider positive. In fact, if you were to measure it with a voltmeter, it would be positive. And that portion below is negative. So one sine wave consists of a positive and negative portion. And the length of the sine wave runs from the left to the right for one complete cycle, which we divide up by degrees. And here's some markers at 45, 90, 135, 180, 225, 270, 315, and 360. Well, the electromagnetic spectrum goes from some very long waves over on the left-hand side. These are the size of buildings and bigger. And most of our radio communications are down in that end of the spectrum, radio electromagnetic spectrum. Microwaves, they're about the size of grains of sugars. Infrared, visible waves give us our colors. Then we have ultraviolet, X-ray, and gamma rays. Radio waves, they have two names. You can name radio waves in terms of meters. This radio wave is 80 meters long. Or you can talk about it in cycles per second. What we'll do then is look at a couple of examples. If we measure a radio wave and it's 30 meters, that is also known as 10 megahertz. M stands for million, hertz stands for cycles per second. So megahertz is million cycles per second. 30 meters is 10 megahertz. 75 meter long wave is 4 megahertz. Well, there's a relationship between those waves. If we look down here on the bottom, we've got wavelength going from short to long. And up here, we've got wavelength in cycles per second. In the length is directly related to the cycles per second. What is that relationship between wavelength and cycles per second? Well, wavelength we'll talk about in meters, and we'll abbreviate it with the sign lambda. Frequency, we'll talk about in megahertz, and we'll abbreviate it with lowercase f. The relationship then works like this. The speed of a radio wave is 300 million meters per second, and that we'll call our constant, letter C. We'll write an equation then that has lambda for wavelength equal to the constant, 300 million meters per second, divide by the frequency in megahertz. So if we plug in our constant at 300 million meters per second, and we divide that by 10 million hertz, or 10 megahertz, what we find is that wavelength is 30 meters long. 300 million meters per second divided by 10 megahertz equals 30 meters. Well, if you go out and look at your car radio, you'll see the dial has an AM set of frequencies and an FM set of frequencies. The FM frequencies we talk about in megahertz. The AM frequencies we talk about in kilohertz. Kilo refers to 1,000, so a kilohertz is 1,000 cycles per second. As part of your exam, you will need to learn some of the prefixes for terms and some of the suffixes. For instance, G stands for gigahertz, M stands for megahertz, which we've already said is a million, K stands for kilohertz, and you will learn these. Hams often work down here in the deci, which is a 10th meter per second, centimeters, millimeters, micrometers, and you will need to learn these as time goes along. We look at all the radio waves that are available. They form what we call the spectrum, and the spectrum's worth a lot of money because radio, commercial radio, television, all sorts of people want to have their radios operating on the frequencies. We start over here at the left end, going from 3 kilohertz to 30 kilohertz. Down here in brown, what you'll notice is that range from 2 kilohertz to 20 kilohertz. That's what we hear. Those are audio frequencies. Then we go 30 to 300 kilohertz. Then we change to 3 megahertz. And then we change up here to gigahertz. As the number, the wavelength decreases, the number or frequency increases. Down here at the very low end, we have VLF, very low frequency, medium frequency, high frequency, very high, ultra high, super high, and extra high. Well, when radio got going originally, the main area was this shortwave section in here from 3 megahertz to 30 megahertz. And people, the early radios, they were pretty impressed. That was a lot of cycles per second, and they called it high frequency. Well, give them a little time, a little more research, a little more money. People were making frequencies that were much higher, and so we had to name something else. We called it very high. More time we got into super high, and more time we got into extremely high frequency. Well, the AM frequencies on your radio, they're medium frequencies, and the FM frequencies are up here at very high. Television has very high frequency and ultra high frequency. That old shortwave, that's basically high frequency. Mobile phones operate up here at ultra high, and the internet crosses between ultra high and super high frequencies. Well, if we go back to that radio for a minute, we look up here at the top, AM, we see it's in kilohertz, and we call that a band. A group of frequencies is a band. Here's another band that's a megahertz frequencies. So the AM band on the radio consists of all frequencies from 53 to 160 kilohertz. For example, with ham radio, we talk about the 80 meter band, and that would be all frequencies from 3.5 to 4.0 megahertz. Well, this chart here shows you all those different frequencies. And if you remember right, hams are allowed to operate on many bands within the electromagnetic spectrum. Here's the low frequency stuff, the high frequency, very high, ultra high, and then we get into super high and extremely high frequencies. Once you have your license, it allows you to operate in different bands and communicate even to around the world. But there are rules, and you have to obey the rules when you're communicating. The license only allows you to operate on certain frequencies, and which frequencies depends on the type of license that you have. However, an amateur radio station may use any means of radio communications that's necessary to provide essential communications. Now, essential communications means we're talking about the safety of life and immediate protection of property. You may do that when other normal communications are not available. So if you come on into a car accident and you need to get first aid, first thing you do is grab your phone and hit 911. If that doesn't work, you can use any radio frequency and any radio mechanism you need to get the message through to save the human life or provide immediate protection of property, such as during hurricanes. Well, having said that, let's get into the radio itself. We're going to make a radio here. Yeah, it's going to be just sort of a little simple radio to play with. But first, we got to do a little bit on some electronics. When it comes to electronics, there are three power players. These are the big guys for the electronic world. Their names are Mr. Volt, Mr. Amp, and Mr. Ohm. And we can put a little drawing forward that shows you how these three power players, they interact. Imagine for a minute, as an analogy, a pipe. And Mr. Volt is trying to push a batch of water through called amps. But Mr. Ohm is trying to stop that. He's squeezing it down. Well, electricity essentially corresponds to that analogy. Volts push amps through an electrical wire, and ohms try to stop them. So since Ohm is on top, we're going to name this the Ohm's law. Mr. Ohm is the controller. He's Ohm's law. Ohm's law basically says voltage equals current divided by the resistance. Voltage equals current divided by resistance. Well, we'll think about a couple of light bulbs here in a second, 120 volt light bulbs. But what we're going to do is we're going to abbreviate voltage with an E. We're going to abbreviate current, amps, with an I. And we're going to abbreviate resistance, that is ohms, with an R. And here we are back to that analogy. And what we find is Mr. Volt is out there pushing with all of his might, pushing with 120 volts. Mr. Ohm, though, on the other hand, is squeezing with 144 ohms. So the question becomes, how many amps can go through when Mr. Volt is pushing 120 and Mr. Ohms is restricting it with 144 ohms of resistance? Well, in order to solve this, we're going to use the equation volts equals amps times ohms. And I'm going to give you a little crib sheet. This little crib sheet will be very helpful when you're taking the test. You can walk in and make this little crib sheet item on your test, and it will help you figure out answers to problems you'll be giving. It's a circle. Top part of the circle has an E for volts. Left part has an I for amps. And the right part has an R for resistance in ohms. So what you do, our question was, if Mr. Volt pushes with 120 volts and Mr. Ohm has 144 amps of resistance, Mr. Ohms has 144 ohms of resistance, how many amps can get through? So to answer that question, you're going to hide this portion of the circle. Put your thumb over it, put your pencil over it, something like that. And you're going to hide where you want the answer and leave exposed what you know. And we know in this situation that there are 120 volts and there are 44 ohms. Volts divide by resistance. And you see the resistance on the bottom. So we're going to take 120 volts, divide by 144 ohms. And what we see is that the current is going to be 0.83 amps. Now let's say the question is, what is the resistance? And you're going to know volts and amps. So resistance equals 120 volts up on top, divide by 0.83 amps down on the bottom, and the answer is 144 ohms. Let's say the exam asks you how many volts. Well, in this case, you've got amps on the bottom and resistance on the bottom, so we'll write the equation. Voltage equals 0.83 amps times 144 ohms. The voltage will be 120 volts. So the example we've been working through is a standard light bulb you might have in your house, 120 volt light bulb. What we want to know is how much power is involved in that. How much power is that light bulb putting out? Well, power we measure in watts. And power is amps times volts. There's that I for amps, that V for volts. Amps times volt equals power. So if we had 0.83 amps and 120 volts, the power we're putting out is 100 watts. So our light bulb at 120 volts is a 100-watt light bulb. Well, light bulbs, their power is measured in watts, but radio transmission power is also measured in watts. So a light bulb has 100 watts. The basic radio transmitters for a home station, say, are 100 watts. Now we're allowed to do a bit more than that, but most all radio communications, even on a global basis, are 100 watts or less. Most of us amateurs, though, don't work up there in full volts, full amps, and full ohms. We work in millivolts, milliamps, and milliohms. That's all the power we got going in our radio. And milli is a thousandth. So a thousandth of 1 volt, a thousandth of 1 amp, a thousandth of 1 ohm. Well, back to our idea of making our own radio here. There's 3 types of radios. We could break them into 3 types. A transmitter to send a signal. We could have a receiver that all it did was receive, or we can combine the 2 and have a transceiver. Well, what you see is there's a lot of parts go into a radio. And somehow, if we're going to make a radio, we got to figure out how we're going to use these parts. And what we're going to do is a little bit of planning ahead of time. We're going to draw out what we're going to do. And on the exam, they will show you drawings, and you will need to interpret some of the parts. Now, drawings for radios, radio diagrams, can be of 2 types. The block diagram, which just simply shows a block to represent what's going on there, a block that would be the outputter, for example. Or they can be schematic with several symbols like we see right here. Well, you read radio diagrams from left to right, no matter whether they are block diagrams or schematic diagrams. So let's start the simple little schematic diagram. Over here, we have an electrical cell, the simplest little battery, if you will, that we can imagine. There's only 1 cell, and we're going to use it. That might be the cell, for instance, you put into a hearing aid. We're going to use it to power a light bulb over here on this side. Light bulb symbol, cell symbol. But we want to get a little bit more, so we'll stack several cells, and that becomes a full-blown battery. Into that line, we're going to put a little resistance. And these here are resistors. They are a type of electronical component that resists the flow of electricity and helps us control the flow of electricity. Finally, this circuit that we're drawing here, we need to be able to control it. So down here on the bottom, we'll put in an electrical switch. Now we got a simple little circuit. We got a battery, and we control the electricity going through it so it won't harm the light bulb. We can do that control with a resistor, and we can switch it on and off. Well, another technique is to make that resistor variable. In a variable resistor, you move an electrical wire back and forth to create different voltages. And here's a type of electrical resistor that we would call a variable resistor. Now, instead of a light bulb, we're going to put in a diode. Diode keeps electricity going in one direction, and diodes have some very interesting properties. They can emit light. Light-emitting diodes, here's a little light-emitting diode, and we are now in this age with light-emitting diodes everywhere we look. In fact, a lot of your televisions are LED televisions, light-emitting diodes. Well, sometimes we don't complete that wire across there. We can run a wire down to an earth ground, or we can run the wire to a metal chassis, for instance, in your TV, and everything in the TV would be connected to the metal chassis, and that would save us a lot of wiring. Transistors are something you've heard about forever. We have transistor radios. They've modernized radio, and transistors can be used to do a lot of things. Here we have a transistor in a system that is wired to the chassis of the little metal box we're working with. In this case, we use the resistor to control electricity into the transistor, which controls the electricity into the light bulb. And that's what transistors look like. So remember this symbol with 3 wires going in and out. That's a transistor. Okay, let's get a little more complex now. We're going to build a very simple crystal radio. This is just a receiver radio. And what we'll do is we'll put a wire up here for an antenna. We'll bring down the signal into a tuning coil and a detector. And between the two of these, we will output a signal into our telephone. And to make a complete circuit, we're going to run it over here to a ground. So this is the symbol of that simple little, what we would call crystal radio. We call it a crystal radio because this detector has a crystal in there that is helping us isolate the radio signal and, importantly, turn it to sound like voices. If we look at that schematic diagram over here on this side, we'll put some earphones, fairly obvious. Then we're going to put in an element here called a capacitor. The capacitor will help us control the signal in the earphones. And over here, we're going to put in a variable capacitor. This one here is indicated by an arrow through the symbol for the capacitor. The capacitor, in conjunction with this inductor coil over here, serve to tune our radio. Now, the inductor coil, that's literally just a coil of wire. We've got an antenna coming down, and we've got a ground going out. Well, this happens to actually be one of the questions on the exam. And here you see an antenna connected to 2 variable capacitors coming down to an inductor coil, which is variable. You see that wire, and you see that it's grounded. Now, transformers that take, say, 120 volts electricity and drop it down to 5 volts for integrated circuits, or up to a voltage that'll support a 100-watt transmission, they're simply coils of wire, and they're indicated by 2 coils of wire. Sometimes we put iron in the center here, and the iron in the center helps move energy across. Now, that energy we're moving across is magnetic energy. So electricity, when you run it into a coil, creates magnetism. That magnetism jumps across here, and that will then be translated into electricity to use on this side. This symbol is the plug-in for 120 volts. Nowadays, those circuits that we used to have to piece together one at a time, many of the components are placed on one little piece. And these are circuit boards such as you would find in a television, but you might find it in your microwave in your kitchen. Circuit boards are about everywhere nowadays, and the circuit boards allow us to do things that would have taken lots of space with using all the old parts. Well, we've got our radio there, but we need an antenna for it. So now we're going to make an antenna. Antennas are really quite simple. They can be made out of anything. I've seen antennas made out of coat hangers, out of heavy electrical wiring, light electrical wiring. There's even antennas made out of light bulbs in light bulbs. Each year there's a group of people that have a contest to see who can do the best communications with their light bulb antennas. Well, to make your antenna, we're not going to try to make one that's as long as a full wavelength. That, for instance, would be an 80-meter long wavelength. What we can get by with is one that's half a wavelength long. And so for an 80-meter radio wave, we can get by with 40 meters. This we'll call a dipole, and there'll be 2 halves to it. That's why it's a dipole. Our wire going to the radio, one part will connect to one side, one part will connect to the other side. We'll use an insulator out there at the end to stop electricity from moving on. So the question becomes, how big of an antenna do I need? Well, you remember back to our equation, wavelength in meters, speed of the radio wave in meters per second, and frequency in megahertz. Well, we can write that equation out, and what we'll do here is we'll pick a frequency. Let's say you wanted to make an antenna for 150 megahertz radio signal. Plug it into the equation. 300 million meters per second divided by 150 megahertz is 2 meters. You would need to make an antenna that was 2 meters long. If we wanted to communicate on a 75 meter antenna, which would be 300 megahertz per second, divided by 4 megahertz for our regular signal, that would give us a 75 meter antenna. But we don't have to have that whole 75 meters long. We can make a half wave or dipole at 37.5 meters, and that will work quite well and is much easier to put up around your home. So that antenna, we're going to make a half wave dipole, but we need to know how much wire we're going to use. So the way you calculate the amount of wire is you take the number 468 and divide it by the frequency in megahertz. So if we have a 4 megahertz radio signal we're going to put out, 468 divided by 4 is 117 feet. You go to the store and you buy 117 feet of wire, or buy 120, just to have a little bit extra there that you can tune. And this equation will be probably on your exam. So remember, 468 divided by the megahertz. And in this case, 4 megahertz. So that would put us on 75 meters of a high frequency signal, and we'd need 117 feet of wire. Well, to that wire, we're going to attach what we call a coax cable. And a coax cable contains 2 wires inside it. There's an inner wire protected by this purple insulation. We'll tie that to one side, the right side in this case. Then there's another woven wire around here, and we'll tie that to the left side, and then we'll put more purple insulation around it. So a coax cable has 2 wires inside it, and the insulation here to keep the 2 wires safe, and the insulation out here to protect it from the outside elements. And we'll take that to our transceiver radio. Well, we've got a radio, we've got an antenna now. Our next goal is, how do we send out a message? Now, you remember that radio wave. We're going to only think about it right now as a radio wave, not an electromagnetic wave. We're not going to think about the magnetism. We're just going to look at the radio wave. And it's very uniform, up, down, up, down. And the sound would be boring. We got to do something interesting with that wave. So what if we take our radio frequency signal, which is many cycles per second. Remember, audio frequency is only down there at 2 to 20 hertz. And what if we could combine the 2 of these? Well, we're actually going to combine them with what we'll call a modulator. That modulator, it accepts the radio wave coming in, and then it lays the audio wave on top of it and combines the 2 of them. Here's our combining point where we lay on the audio wave, and now the radio signal is carrying something interesting like music. Well, there's a couple of ways we can combine them. One way is to change the up-down amplitude like you saw on the previous slide. The other way, though, is to make frequencies lower or higher, wider or closer apart. This one up here where we change the amplitude, we will call amplitude modulation. Down here where we make the frequencies lower and higher, we'll call that frequency modulation. And these are 2 major types of radio communications, as you learned from your car radio long ago: amplitude modulation and frequency modulation. There's that car radio. Remember, amplitude, AM on top, frequency modulation on the bottom. When we send out a radio wave, we say that it is propagating through space. So let's take a little look at how propagation occurs when we're sending a radio wave. We have to get it through the atmosphere, and there are various ways that we can get a radio wave through the atmosphere. Let's say we got 2 towers set up there, and we want to communicate from here to here. Well, line of sight, that's no problem. The radio wave just flows straight across to the other tower. But what if that other tower is moved? We've got a skywave that goes between 2 that are line of sight, but what if we move the other tower over here? Now when you shoot a skywave out, it misses this one. Well, it turns out the curvature of the Earth stops signals uh, and sends them into space, so we'll call it a space wave. And the curvature of the Earth at about 3.7 miles is enough to block signals from going elsewhere. And with a handheld, you can usually get about 5 miles without being up in the air. But the curvature of the Earth will block that signal, and that wave just goes out into outer space. Well, ways around that. Build a bigger tower so it's now back in line of sight. Another way around it would be to send a signal out that hits the ground and bounces up. When it bounces up, it connects to the other tower. And this sort of wave we will call a ground wave because we used it on the ground. Now, earth, soil is not the best of ground waves, but water's a lot better ground wave. So people on the coast find communications around the world much easier than those of us that are landlocked here in Montana. Well, let's look at another way we might increase the range of our signal. The ionosphere, that portion of the atmosphere 30 to 260 miles up, can refract radio waves. So where the space wave misses, what if we send the space wave to the ionosphere where it gets refracted back down, and now we can communicate halfway around the world by taking advantage of what's called refraction, where the radio wave hits into the ionosphere and is bent in the ionosphere till it's sent back down to Earth. Well, when we do that, there's what we call a skip zone. The skip zone is where the radio wave does not hit. So our wave going up here talks to this person well, but everything here in the skip zone, they're not going to hear us talking. That ionosphere is a powerful tool, but it's kind of complex. You have to have just the right frequency to get it refracting on that particular day, that particular time, that particular season. If the signal is too low of a frequency for that time, it gets absorbed. If the frequency is too high, it blasts its way on out into outer space and it passes through. Well, this little illustration is just a consolidation of everything I've been explaining. We see ground waves bouncing off to the tower, space waves going straight through, space waves refracted low down, space waves refracted higher up for a greater distance. Ones going into space that just plain get absorbed because frequency is too low. And these that are passing to outer space are what we use to communicate with the International Space Station, the Mars orbiter, and even our satellites that are leaving the solar system still send radio signals back. Living in Montana is a great honor. It's an incredibly beautiful state. And this is the view out my front window of Electric Peak. Electric Peak got its name because lightning tends to strike up there a lot. And what I'm going to do is give you a very special pair of glasses so that you can look into the outer space above Electric Peak. And we're going to take a look at the propagation above Electric Peak. So put your glasses on, folks. Look closely. And what you'll see is there are clouds up there. There are 4 bands of clouds that go up above the Earth. Now, those clouds are made up of electrons. The fewest electrons are down low, and as you go up higher, each layer gets more and more electrons. How come? Well, let's name these layers D, E, F1, and F2. And let's look what happens. As the sun blasts its way through, we get X-rays, mid-ultraviolet, far ultraviolet, extreme ultraviolet, visible light, infrared light coming down. These lights interact with oxygen and nitrogen molecules and knock off electrons. Well, as you see, the upper layer has all the wavelengths going through. But as you start getting down, wavelengths are absorbed. And for instance, the extreme ultraviolet, very, very little of it would ever get down to the Earth. So what that means is there's more electrons in the upper layer. Let's say, for example, we'll send up a radio wave, kind of low frequency. It gets to the D layer and it is absorbed. No successful communication. Let's use a little higher radio frequency it blasts through the D layer, hits the E layer, where it too gets absorbed. Again, no effective communication. Let's use a little higher frequency. This time it gets up to the F1, but there's enough electrons up there that it's for refracted down, and we can make successful communications. Well, let's use one with a little bit more frequency, higher frequency. It blasts through DE and F1 and hits the F2 layer, where it is also refracted down, and we get a greater distance of communications. But refraction takes those two waves and sends them back to Earth. Let's go to a higher frequency. And with that higher frequency, whoops, it blasted through DE, F1, F2, and we're out communicating with the Mars rover on Mars. The high frequency penetrates and gets us out. But what if we don't want to penetrate? Then we've got to have a lower frequency. Well, here's what happens. There's my house right down here in the center. There's Electric Peak over there, and sunset. Well, remember, the sun was blasting through all these layers, and suddenly it goes dark. There's no waves from the sun to create the D layer, so it disappears. None for the E layer, it disappears. F1 and F2 meld together. So what happens if we use those saved radio transmissions we used before? That first one we set up now gets clear up here. It's refracted off all those electrons on F layer. A little higher frequency, still refracted. A little higher frequency, still refracted. A little higher frequency, still refracted. And we're getting out there further. You probably experienced, maybe growing up, nighttime, your radio communications improve in quality and you get radio signals from farther away on that car radio. And if we go to a real high frequency, it still penetrates to outer space. Well, we have what we call the MUF. MUF is maximum usable frequency, and that is the highest frequency we can use and still get refraction and communications on planet Earth. MUF is a fair question on your exam, folks. Well, the E layer is a strange layer, often called the magic layer. We call it sporadic E, and that's abbreviated E with a sub S. Sometimes all the E layer just doesn't disappear, and a radio signal will bounce off it and give you communications at great distance, but there will be a skip layer in there, skip zone, where the radio communications won't occur. Now, I've set on what we call Beartooth Pass on the northeast corner of Yellowstone area and communicated into Spain, bouncing radio signals off the sporadic E layer. So Electric Peak, well, that's magic to me, but what goes on above it is magic to the radio. This illustration is a comparison to give you an idea, a one-piece crib sheet, if you will, of what's happening. In the daylight, we have D region, E layer, F1, F2. As the sun disappears, it gets dark, and DE disappear, maybe some sporadic E, F combines into one layer. Now you notice these layers are below the satellites, but they're well above where planes and balloons go. Meteorites tend to be burning up pretty well by the time they get down to the E layer. Let's think about radio waves for a minute. We talked about some that are high frequencies, some that are very high, and some that are ultra high frequencies. Well, each kind of radio waves has very different properties and very different behaviors. And as you work in radio, you will learn what these properties are and how to use them to your advantage. To give you a little bit of an idea, I'm going to show you a comparison. We have a system that keeps track of radio communications, and this system is working on the 20-meter band here, and it's showing that 20 meters is very active between the United States and Europe in the daytime, but as the nighttime shadow advances onto it, the 20-meter starts to fade out, and by midnight, 20 meters just isn't any good. And here, as the shadow is leaving, it's starting to build up. So we generally think of 20 meters as a daytime radio frequency. This is 40 meters, and notice 40 meters is not working in the middle of the day, but Europe, as the shadow comes in, is able to make great communications into the Japan, the Pacific area, and the West Coast of the United States is able to make great communications there. So at this time, the 40-meter band is working well at night. We think of it as a better night band. Propagation is something you'll learn more about as you work with radio waves, and you have to utilize propagation to make your worldwide communications. So how do you get on the air? How do you actually start working with a radio? Well, all you need is your phone. The cost of that phone, well, you probably already got it. But there's a set of software called Echolink, and that software is available only to licensed hams. You can load it onto your radio and use your radio as a phone and talk all over the world. Another way to get on is a handheld transceiver. You can get these nowadays for as little as $40. They work on 2 meters and 70 centimeters. We have what we call single or dual band. Single would only be 2 meters or 70 meters, where a dual band would be both of those. Now, we call those HTs. That's handheld transceiver, or some people will call them handy talkies. And they work for FN communications, digital communications, and sending messages. Typically, they're only 5 watts. Now, if you're familiar with the people that work out in Yellowstone observing wildlife, this is the same power and, in general, the same type radio we use out there. Or you can go mobile. And for mobile, you need a magnetic antenna on your vehicle. That's me with my magnetic antenna. And a setup inside. Here's the radio setup inside. Typical mobile units are VHF and UHF and about 50 watts in power. Or you can set up a base station in your home. And the base station, usually more on high frequency stuff, has to have a power supply and an antenna. We can amplify our signal. In fact, when you're a fully licensed at all levels ham, you can communicate by taking a 100-watt signal and amplifying it to 1,500 watts. And of course, you need your transceiver. A tuner to work with the antenna is great. And nowadays, we're starting to use PCs with our radio communications. Well, the big goal of the radio operator is, how do I increase my coverage? Key elements to that: bigger the antenna, better the coverage. Higher the antenna, better the coverage. Or the more powerful radio. But it turns out bigger and higher antennas are much more important and cost effective than a powerful radio. The Amateur Radio Club here at Gardner, North Yellowstone Amateur Radio Club, we maintain a repeater high up on the side of Electric Peak, and we call that repeater the Eagle's Nest repeater. So what's in a radio? Here's a little block diagram of the radio. And the radio itself has an antenna coming into a coax feed line. There's a transmitter and there's a receiver. There's a little switch in there. You cannot transmit and receive on the same frequency at the same time. So what this switch does is, when you want to transmit, it turns off the receiver. When you're not transmitting, it turns on the receiver and turns off the transmitter. Principle: you can't transmit and receive on the same frequency at the same time. Well, for our repeater, we're going to do something different. We're going to put in a duplexer. Now, the duplexer works between the transmitter and receiver, and what it will do, it will allow us to receive and transmit at the same time by using 2 different frequencies. So this is critical. We can receive and transmit at the same time, but we'll have 2 different frequencies operating. Well, this is kind of diagrammatic representation of our Eagle's Nest repeater. We got a tower up there. We got an FM transceiver down here. We put a signal out into the tower and it sends it out. Now let's say we've got me over here on the side with a handheld, and we've got someone over here with their mobile in the car. Well, it's too far for my little handheld to reach across there. So what I'm going to do is I'm going to transmit up to the tower, and the tower is going to take my signal and transmit it to the car. Remember, it's going to do this same time, can't be the same frequency. So I will transmit up at 146.38 megahertz. The receiver will pick it up at 146.38 and retransmit it at exactly the same time, but on 146.98. So when I'm talking, he's listening by using two different frequencies. When he wants to talk to me, he radios the tower and he uses 146.38, and the tower downloads it at 146.98. Talking from the car at the same time I hear it, but two different frequencies. So that's how a repeater works. My little 5 watts gets out to him many, many, many miles away by use of a higher antenna, and he sends back to me from his car. Well, in Montana, we have a very special repeater system. It's called MARLA. It's the Montana Radio Link Association. Montana Radio Link Association has repeaters that follow I-90 across, then split and go north and southwest. And if you can reach one of the repeaters, it sends your signal out to all the other repeaters in the state. Very important for emergency services during bad weather in the wintertime, summertime, whatever. Now, we said that we could increase our radio coverage by bigger antenna, higher antenna, even a bit by more powerful radio. But what if we included the internet into this equation? So what we'll do is we're going to use what we call Voice over Internet Protocol, VoIP. And there's several VoIP systems out there. They have the names of Echolink, D-Star, DMR, ILRP, Fusion, WiresX, and P25. Well, Echolink is one that's available only to hams, and any hams can use the Echolink system. The Echolink system works like this. Here is our Eagle's Nest repeater, for example, and our FM transmitter down there. And we have connected it now to a computer. Well, over in Russia, there's another guy that's got a system set up the same way. He's got a repeater connected to a radio, connected to a computer. And this person out here in the car wants to talk to this person over here. Problem is, that's about halfway around the world. And guess what, folks? It is not going to work. So we turn on the computer, link it to the internet down here with software called Echolink software, and we send a signal over the internet to the other side. Car radios tower, tower sends a signal to the computer, computer sends the signal now by internet to this computer sends the radio tower here sends out a radio wave to the car, and we're talking halfway around the world. We can do something else too. We can link our telephone into the internet, and now I can call on the internet to either one of these stations halfway around the world. So Echolink looks like this. This happens to be AE7DU, is the Echolink repeater that is sitting on the Red Lodge ski area. And when I wish to talk, I push the transmit button, a screen comes up like this, and I'm transmitting away to wherever I choose to transmit. And Russia, of course, is a favorite topic, to get a radio signal halfway around the world into Russia. Before playing with your radios, transmitting through radios, we've got some rules, we've got some regulations, and we've got some ethics that we need to deal with. When it comes to rules, the first rule we deal with internationally around the world is the internationally accepted language is English. We're so lucky here in the United States. Now, other countries can talk in their own language, but if they want to communicate worldwide, they have to go to English. We also encourage people to use the phonetic alphabet. Radio signals are not always good, and sometimes you need to spell out words to communicate, and we'll use a phonetic alphabet. The phonetic alphabet works like this. If I use Alpha Bravo Charlie, I can spell out cab. Charlie, Alpha, Bravo. And we have 26 letters, of course, in the phonetic alphabet, and you'll learn the words to use there. Everybody uses the same words, so it makes it easier to understand when you're spelling something out. Indecent, obscene language is prohibited on the amateur radio frequencies. Be good, folks. You would never willfully interfere with somebody else's radio signal, such as talking over them if you have a more powerful radio. And you may not use codes, plain language only. There are some exceptions to that. We can't, for example, use 10 codes like the police do, but there are a few little code words we use. And the other exception is control commands. Control commands are used to fly model airplanes, boats, and control the space station. Well, speaking of the space station, let's go there. Outer space. The hams have over 240 satellites of their own orbiting the planet Earth. The most favorite satellite there is the International Space Station, and all the International Space Station astronauts are ham radio operators, and they take great pride in flying over and talking to us on the ground. And surprisingly, that 5-watt handheld transmitter will allow you to talk to the International Space Station. Of course, put a better antenna on it, it'll work better. The other thing that hams have are called CubeSats, and these are nothing more than repeaters in the sky. They're super small. They're 10 centimeters by 10 centimeters by 10 centimeters as a cube, and they allow us to communicate around the world. Who can transmit on those satellites? Anybody with a technician license, and that's the very first license you get. Any license of a higher grade than technician, obviously. Well, there's some etiquette for using a repeater. On the repeater, you always listen first for a couple of minutes to see if somebody else is talking. And you would never call CQ. Now, CQ is one of the abbreviations we can use. It stands for calling all hams. Calling all hams, will somebody respond to me? And we never do that on a repeater. On a repeater, you listen first. And when you go to transmit, you talk as if you would with a friend out there on the street. Hey, Tom, how are you doing over there today? Hey, Tom, is that bacon I smell cooking? You just talk as you would out on the street. One way to get radio experience on the repeaters is to join a net. Now, a net is a group of hams who meet at a regular time. And here in Gardner, we have a net every Thursday night at 7:30. In Billings, they have a net every morning at 8 o'clock in the morning. So join a net, and that will allow you to listen to others and learn your etiquette for being on a repeater. Get your ticket. What does this mean? Your ticket is your radio license. And to get your ticket, you will also get your call sign. My call sign is K9YNP. Well, you got to go to the Federal Communications Commission and take their exam in order to get your ticket, get your license. Once you got your station license, though, it designates that you are the control operator. You're in control of everything that happens to happen there, and you are responsible. If that radio is being used illegally or in a unethical manner, you are responsible. So hams are very conscious of this, and we do a very good job of using our radios. The transmission privileges you have on your radio depend on your class of operator license. There are 3 classes I'll talk about more, but they're technician, general, and extra. The maximum power the technician can use is 200 watts. There are some exceptions to that, but we won't worry about those here. Ham radio operators break up the United States into zones, and those are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And those zones are subunits of the International Telecommunication Zones, ITU 7, ITU 10. Now, the ARRL, American Radio Relay System, has a contest called Work All States. And once you work all 50 states on your radio, you get an award, you get plaques to put up on your wall. And you might remember at the beginning, I talked about the 7QP party. That's where we communicate in all states within the 7 category. When you get your station license, you will be issued a call sign. That's what we call a 2x3. 2 letters, a number, 3 letters. There are other types of call signs. There's a 2x2. And this happens to be a 1x2. And there are 1x1s, K7X, 1x2, N7LL, and you even have 2x2s. You only get these short call signs as you get higher grade licenses, though. But anybody can go after a vanity call sign once you have been licensed. So my vanity call sign is K9YNP. Canines are dogs. The big dogs of Yellowstone are the wolves. YNP is Yellowstone National Park. When may you start transmitting? Well, the FCC will list on their licenses database your call sign generally within 48 hours after you pass the exam, and you can start transmitting. Your license is good for 10 years, and it's going to cost you $35. When you're transmitting, you have to identify your transmissions with either continuous wave, that is the name for Morse code, or by voice communications. You must identify every 10 minutes and at the end of a communication. You transmit your call every 10 minutes and at the end of that communication. Ham operators like to verify with other hams if they've talked to them, and we have what are called QSL cards. QSL cards are pretty spectacular. The one up here in the upper left is for K9YNP, that's me, and it shows my Yellowstone background. As you can see, each ham is very individual, and they create quite interesting QSL cards. One of my favorites is one of my communications with NASA right here, the NASA Radio Club, and they sent me that QSL card. Well, in order to get your license, you need to take an exam. And exams are offered right now in this part of Montana in Gardner, Bozeman, and Billings. There are exams for 3 levels or classes of radio operator. The beginning class is technician. That gives you privileges to communicate on the 10-meter and 6-meter bands, all VHF, all UHF, and the microwaves, which were those super high and extremely high frequencies. Your general license takes a little bit more knowledge, but it gives you more privileges on the HF bands and gets you more into world international communications. The extra license gives you all the portions of the high frequency band. It focuses more on radio theory. Most of what goes on in Montana goes on VHF and UHF. Most of the people talk there. Radio and emergency communications go on there. So once you get your technician, you've opened a wide new world. Remember that frequency chart? Well, this is the frequency chart again. And if we look at it right here, you'll see E stands for amateur extra, A for advanced, G for general, T for technician. So if I go up here to the 10-meter band, what I see is that the extras, the advanced and generals can use this portion up here. And the colors then, red is data communication, green is a voice. So down here we can only send data, but up here we can communicate with voice. Down here we have the technician license in yellow, that's single sideband communications, and red is data. So the technician license opens up all of the 10-meter, 6-meter, 2-meter. 2 meters the prime one where everything happens, 1.28 meters, 70 centimeters UHF. This and 2 meters are the key two, but it takes you down into all these super high and extra high frequencies. You as a ham operator can construct and run your own Wi-Fi network. And the interesting thing is hams can use more power on their Wi-Fi networks than can commercial operators. Okay, to take the exam, the initial license is 35 questions. They're multiple choice 4 questions or 4 answers per question. And there are about 400 questions in what we call the exam pool. These questions are published. They're public information for you to study what the questions will be on your exam. Well, there's 2 ways to go at it. One is just to memorize the exam. The other is to learn some content. Tonight, by paying attention to this video, you've been learning a lot of content. Most people memorize the exams. That's the quickest way to do it. If you'll take 1 week before your exam and spend 1 hour per night, I recommend 2 hours, that's better, you're going to pass that exam. The other way is to learn content by using a lot of resources. You'll be better prepared for the next level up if you learn content, and you'll be a better radio operator. In reality, probably most of us do both of these to a certain extent. If the exam's coming quickly, memorize the questions themselves. There are 10 categories of questions: rules, procedures, radio waves, amateur radio practices, electrical components, your station, operating activities, antennas, and safety. And we've talked a little bit about the first 9. I haven't talked much about safety tonight. These 10 categories, the exam will take questions from each category. So on rules, there will be 6 questions. On operating procedures, 3 questions. On amateur radio practices, only 2 questions. So you're not going to get stuck trying to have to answer all the questions and say frequencies and deal with all that math. You only have at the most 2 or 3 or 4 questions in a category. Well, let's go through some of the resources for your studying. ARRL at ARRL.com has one tab for licensing, education, and training, all sorts of good information there. Another tab for getting licensed, and that has the exams there. I highly recommend Ham Test Online and Ham Study. I'll come back to those in a minute. You can download the entire question pool at this address, ncvec.org, and then the rest of that information. I believe the best way to pertain or get ready for your exam is to go to Ham Test Online. It's going to cost you about $35, but they will have all the questions there, and they will group the questions and give you a little crib sheet beforehand explaining it, and then they will go through the questions showing all the question answers and the correct answer. Ham Test Online keeps track of where you're weak, and it will throw those questions at you later. And once you get to where you're answering most of the 400 questions correctly, you can take random exams there. The hamstudy.org also does similar thing, although they don't have the good crib sheets, but they give good exam preparation. And more importantly, they are one of the prime sources for figuring out where exams are going to be given. I gave you 3 places here in Montana, but what if you're in California? Go to hamstudy.org and it will come up and say, where would you like to take an exam? And you click on it and see where and when exams are going to be given there. There are a lot of excellent books out there. ARRL sells the Ham Radio License Manual, 3 levels, level 1 technician, level 2 general, level 3 amateur. Nice book called No Nonsense Technical Class License Study Guide. Technician Class License is another book. All these are available on Amazon, or you can go to ARRL to get their license manual, but you can buy everything on Amazon. Now, the American Radio Relay League puts out magazines called the QST, and there's another organization puts out one called CQ. These are great resources, especially after you get your license. I highly recommend everybody join ARRL. And the ARRL has sections all across the United States. The Montana section includes the whole section of Montana. The section manager is Paul Stiles. He's in charge of everything that happens here for ARRL. And Paul's open to all questions you might want to throw at him. There's his phone number, 406-671-7092, or his email address, which is his call sign, kf7soj@ARRL.org. Other resources include clubs in the area. One of those is the North Yellowstone Amateur Radio Club. That's the club in Gardner. And Gardner is in Park County, Montana. Park County, Montana has an amateur radio emergency services called PCARES, or Park County Amateur Radio Emergency Services. Over in Billings, the club is the Yellowstone Radio Club, and it has a website, ka7efa.net. There's also a amateur radio emergency services there called Yellowstone. So that's Yares, Y-A-R-E-S. Bozeman has a radio club, the Gallatin Ham Radio Club, and their website is gallatinhamradio.com. One of the resources is in Billings and in Gardner, we offer a new ham class. Our two clubs, once you've got your license, about 2 weeks later, we have a class that goes over stuff and actually gets you up and transmitting on the radio. So if you get your license in those areas, take advantage of the new ham class. Join a local club, folks. It provides a lot of stuff. The friendship, camaraderie. You find people there that can tell you all sorts of things about radio. They get you going. It gets you into public service. Competitions or radio competitions that help us strengthen our skills. Well, I want to acknowledge several people tonight because this program is only possible because of the people that have served as Elmers. Now, Elmers are the term radio operators use for mentors, and several folks in this area have been my mentors for one aspect or another of the radio communications. If you need to get a hold of me, go send an email out to k9ynp@arrl.net, or simply put the Google to it. You'll find me. I'm pretty public on the net. Well, I want to thank you for joining me tonight, and I hope this helps, and I wish you all luck in getting your exam passed and having your radio license. I look forward to communicating with you on the air. We would say 73s in radio communication. A 73 means best regards. So 73, my friends.